Hello everyone, welcome back to Explore Electronics. In this video, let's see the instructions of 8051 microcontroller and let us look into each and every instructions with examples. Then we have logical instructions. Logical instructions in the sense logical AND, logical OR, logical XOR, these kind of operations. ORL corresponds to OR operation. It is a bitwise operation. Bitwise in the sense, suppose we are doing OR operation between 1010 1011 with 1110 1111 means here we are doing bitwise. First we need to consider this 11 is 1, 11 is 1, 10 is 1, 11 is 1, 0 OR with 0 is 0, 1 1 1. This is the result of OR operation. Bitwise means we are doing these two bits into consideration. We are doing OR operation between these two bits, these two bits like that. So here we require two operands. This can be one operand with some register A content. This can be some R0 content. We are doing OR operation between these two. This will be the output or the result. This will be stored in accumulator again. Similarly, ANL. Here ANL is AND operation. In the same way as I explained OR, AND operation is also going to be executed and the result will be stored in operand 1. Then similarly we have XOR operation. This is again a bitwise XOR. Here we need to specify one register with other register. This will be doing exclusive OR. Exclusive OR means the truth table for exclusive OR is if we have 0 0, output will be 0. If 0 1, any one of the inputs are 1, output will be 1. 1 1 will be 0. This is the output of XOR gate. If you have OR gate, then we will get 1 1 1 here also. This is the difference between XOR as well as OR. This is exclusively OR. So XOR will be using an opcode X R L A comma Rn. The result will be stored in A again. Then we have CPL. This is complement. It will do a complement of the operand what we are going to use here. CPL A means A is a register which will be containing some value. Complement of that means it will do ones complement, we can say. Ones complement means 11001010 is the content present in A. After CPL A is executed, it becomes exactly the reverse of that value, means complement of that value. This is ones complement. Then we have clear CLR with a register. If you are going to execute CLR A, what it is going to do, whatever the content present in A, that will come back to 0, 8 zeros, means 8-bit register. Then we have rotate left. This is rotate accumulator left. RLA means rotate left with the accumulator data. So accumulator will be having 8-bit of value. Let me write 0th position, 1st position, 2nd, 3rd, 4th, 5th, 6th and 7th position. When we are going to execute RLA, this is rotating left, means it is going to shift 0th position to 1st, 1st position value to 2nd, 2nd to 3rd, 3rd to 4th, 4th to 5th, 5th to 6th, 6th to 7th. Where this 7th bit should go, it would go to 0th position. This is how the rotate left is going to work. Similarly, when we are going to execute RR, rotate right, in the similar way, these bits are going to be shifted right and the 0th position bit will come back to the 7th position. This is rotate instruction. Then rotate with carry. Rotate left with carry, rotate right with carry. Here you can observe, as I said, the shifting will happen to the left side, but we need to consider the carry when we are rotating the last bit to the 0th bit. We need to consider carry over here. This is the 0th bit. Before the 0th bit, we will be having a carry flag. This carry will move to 0 and the 7th bit will move to carry. Similarly, RRC, the 0th bit will move to carry and from carry, we are going to get the value at the 7th bit and these bits are going to be shifted. And remember, only once it is going to do, only one shift or the rotate is going to be executed when we are going to execute RRC or RLC or RR, RL. Then branching instructions. We have different branch instructions. These branch instructions are required when, suppose if we have some 10 lines of code like this, we are at this position. Depending on some condition, we are going to check and we need to jump to this line. what we are going to do, here we are going to check suppose a carry is generated or not. Then if carry is generated, I need to jump to this line. Then jump instruction with carry, jump if carry is set can be used. In those cases, the jump instructions are the branching. We are branching the execution to this line. That is what the branching instructions are. So let us see. Jump instruction. Jump instruction uses a register over here. Jump at the rate a plus dptr. Means this register will be a address. Usually this will be an address of some instruction. This address specifies this line. So once the jump instruction is executed, this a plus dptr will be indicating particular line, and from this line onwards the code will be executed. In these cases, labels are going to be helpful. And you can see JC, this jump instruction without any condition, we are just jumping to the branch of the code. JC will be used with the carry. JC, if we are going to specify some address over here, this address will be this address will be specifying somewhere here, and JC checks the carry flag first. Jump if carry is equal to 1. This is the condition. If carry is 1, then only this address will be fetched and the branching will happen. Otherwise, if carry is equal to 0, it will continue the next lines of code for execution. Here you can see REL address. This is a relative address. What do you mean by relative address? It is a offset address. This offset address is a 8-bit signed value which is added to the program counter. Program counter will be having the execution instruction address. So this program counter will be added up with this offset, and then the branching is going to happen. Then JNC indicating jump if carry is not set. If the carry flag is 0, then only do the jump operation. Otherwise, the normal execution is going to be executed. And similarly, we have DJNZ. Here, decrement and then jump if not 0. Here, we need to observe DJNZ. We will be having a register over here, comma, address will be specified. Means to this address, the branching should happen. Means the jump should happen to this particular address. And this decrement will be for this register. This register content will be decremented, and then we are checking if it is not 0. If this register value is decremented by 1, if the result is other than 0, something like 4, then only it will branch to this address. If this after the decrement, if this register becomes 0, then this condition fails. Not 0 condition fails, and the next lines of code will be executed. This is how jump, decrement and jump if not 0 is going to work. Then CJNE, compare and jump if not equal. Here also the jump instruction where it should go to this particular address, or this will be the relative address, you can say. I am just saying this is the address for your reference. So here there are two operands. It is this opcode is compare and jump if not equal. Jump should happen only when these two are compared and these two are not equal. If these two are not equal, then only the branching will happen. It will directly jump to here. You can see here A is compared with 99H. A will be having some 80H. So if you are going to compare these two are not same. Then jump if not equal. These two are not equal now. So it will go to the next. This is how the compare and jump instructions are going to be used. Then we have jump if accumulator is 0, jump if not 0. JZ relative address. If you are going to use JZ, it will directly checks whether the accumulator is 0 or not. Here we are not specifying the accumulator over here, but JZ instruction internally checks A first. What is the content of A? If it is 0, it means jump instruction is going to be executed. If J and Z is used, it will check for jump if not 0. Other than 0, if you have any other value, then jump instruction is going to be executed. Then we have short jump and long jump. This short jump is having a opcode SJMP. Long jump will be having a opcode LJMP. You can see here short jump, again we are going to specify the address. Similarly, long jump also we need to specify the address here. This shard jumps unconditional to the address specified. This address can be anything, but this address should be within -128 to +127 bytes of instruction that follows SJMP instruction. This LJMP is a long jump, means here we are going to specify some code address. This jump unconditional to the specific code address what we are going to give. The difference between these two is that this indicating address within the range from the execution. Suppose PC will be at this location. We can expect a jump using SJMP -128 bytes from this PC located address plus 128 bytes from this address. Beyond 128 and 128, we need to use the long jump. Usually that will be the code address. And then AJMP. This is absolute jump within 2K block. Means here you can observe this AJMP instruction unconditionally jump to the code address what we are going to specify. The new value of the program counter is calculated by replacing the LSB of the program counter with the second byte of the instruction, AJMP instruction, and replacing bits 0 to 2 of the most significant byte of the program counter with 3 bits that indicates the page of the byte following AJMP instruction. So let us discuss how this AJMP works exactly when we are looking at this instruction used in some code. Now you just remember this absolute jump instruction will be used within the 2K block, and it is going to alter the program counter value replacing the LSBs. Then LCall, this is call instruction. The previous thing what we have seen in a branching is jump instruction. Jump and call are the two types here. LCall is a long call, ACall is the absolute call. LCall, again we need to specify the code address. This calls a subroutine program, means there will be subroutine programs will be there. When we are going to call that subroutine into your microcontroller code, then we are supposed to use LCall. This uses a stack pointer, and it pushes the value onto stack pointer, and then program counter will be set to the value which called by the LCall, and then execute the subroutine. Similarly, we have absolute call. This absolute call, again as we seen in the previous case, it is within the 2K block of address. For more information, you can read these content. Then we have RET instruction, return from the subroutine. Whenever we are going to use LCall or we have seen ACall. In these cases, whenever we are going to call the subroutine within our microcontroller to execute, then we need to use RET to return back to the execution of lines. We need to come back to that normal coding. So in such cases, we need to use return instruction after LCall is going to be executed. Similarly, RETI, return from the interrupt. This will be used when interrupt service routine is used. That is a concept of interrupt. We need to understand there are different types of maskable, non-maskable interrupts. So when there is an interrupt service routine comes into the picture of execution, then return from that interrupt is going to be happen through return from interrupt opcode. Then we have bitwise instructions like JB, jump if bit is set. Here this jump B is going to this relative address if the bit of this address is going to be set. It means, how to understand this? JB, this instruction branches to the address specified by real address, means it will jump to this address only if the bit indicated by this address. In this address we need to check what is the bit. If this bit, the particular bit is specified, if this address in that particular bit is set to 1, then only the jump will happen, otherwise jump will not happen. Similarly, jump if bit is not set, it will jump to this address by checking this address with respect to a bit whether it is not set, means it is 0 or not. Then we have jump BC, jump if bit set and clear bit. Here you can have an address to the jump. To this address it will jump, and it will check whether a bit is set over here or not. And then what it is going to do, Before branching to this address, this instruction will clear the bit of this address. It will make it to 0 if it is 1. It will check if it is 1, then it will come to know that we need to branch to this address, and it is making that address bit to 0. This is JBC. So these are the different instructions we are going to use in microcontroller coding. In the next videos, let us see more concepts on this microcontroller. Thank you.